Assalamu alaikum جميعا. My name is Hamood Alharthi. I am a final year physics student and the leader of Al-Baywan Club of Philosophy of Science. Before beginning, I want to thank Prof. Hisham and the rest of us, Dr. Ali for attending, and everyone for attending today, and SBG for their collaboration. Okay. صوتي واضح؟ So I will start on a brief history from classical mechanics. Classical mechanics was under the assumption that if you know the initial position and momentum of exactly of a system of particles, or even if for a single particle, then you can predict the future with infinite precision. This notion of determinism was pushed very hard by Simon Pierre Laplace, or Pierre Simon Laplace, the French mathematician and physicist. He had a statement. He said, "The present state of the universe is the effect of its past and the cause of its future." So the current state of the universe is nothing but the effect of its past, and it will be it's the cause of its future. Okay. When Laplace was theorizing or pushing this philosophical determinism in science in general, he was under the influence of classical mechanics and the propositions, the philosophical propositions that followed from classical mechanics. In his famous book, Celestial Mechanics, he did a formulation that allowed us to calculate ellipses and the orbits of planets with precision for 200 years, 100, 200 years, for centuries. So he was supported by classical mechanics, by the framework he was working with. Laplace actually did a thought experiment, very well-known thought experiment. He said, if you give me, or if imagine there is a creature, an intelligent creature, if you give him all the information, the current state, position and momentum of all the particles in the universe, and assume he has infinite computational power, then you can predict the whole future of the universe and the whole past of the universe with high precision. And then this was in the 19th century, and in the last century we know what happened. Started with Max Planck and his proposal. He quantized the black body radiation, and then Einstein came along and quantized the whole EM spectrum, electromagnetic spectrum, and then quantum mechanics started from there. So this notion of determinism was pushed out and was refuted by quantum mechanics. Okay. Today we will go to, or we'll talk about one particular principle in quantum mechanics, which is the Heisenberg uncertainty principle. It's basically said that you cannot measure the particle position and momentum with infinitesimal precision. And there is a quantitative relation that sets a lower bound to your uncertainty. So your uncertainty in position multiplied with your uncertainty in momentum should be more than or equal h bar of 2. And h bar is a constant, reduced Planck constant, very, very, very small constant, but it's a finite. Okay. In this seminar, or in this, yes, in this seminar, I am claiming that this principle has a classical origin, at least from conceptual part, conceptual classical origin, and it can be deduced, at least conceptually, from classical, from the framework of classical mechanics. Okay. Okay, so the agenda for tonight will start, which is the main topic. We'll talk about the axiomatic. We'll do an axiomatic analysis of the uncertainty principle, and then toward the end, there is a note, something, a realization that I came at from doing my FYD project related with the conservation of uncertainties. Okay, so let's begin. Now, I will start by defining what axiom is. Axiom in general, in science in general, refer to an assumption, specifically in logic and mathematics. So when we say axiom, we refer to, or we refer to a fundamental assumption, an assumption that your theory can't be true without it. So, in any scientific theory, you start with your assumptions, certain assumptions. For example, Einstein with his special relativity, he started with two assumptions: that the laws of physics are irrelevant, or are true in all inertial frames, and then the speed of light is invariant in all inertial frames. So those assumptions are called the axiom in mathematics, especially. And then from your assumptions, you build up your theory. You start deriving and theorizing your theory, and then finally the theorems are the fruits of your assumptions. So you start from here, the theory, to derivations. It might be mathematics, it might be another kind of derivations. In philosophy, it would be just words. In physics, it would be equations and a mix of equations and concepts. In math, it would be only equations and mainly equations. Okay. So there's an analogy. Axioms we can read. And they are like the roots of a tree, the ground, the whole ground actually, the ground that you start your theory with, and the core of the tree is your derivation of theorizing process, and the fruits, or the leaf and fruits, and the single are your theorems. Okay, and this seminar will adopt 5 axioms before proceeding. We will use them to justify or to analyze the uncertainty principles. The first 2 from logic, and the second 2 are from physics, and the last one is a set of axioms from mathematics. We will just denote them by one set. Okay. So we'll start with the famous Schrödinger cat's experiment. Erwin Schrödinger in the 1930s proposed a thought experiment. He said, imagine there is a cat in a seed box with a radioactive source and a Geiger counter, which is a radiation counter, and connected with a hammer. Below the hammer there is a poison, a bottle. Because radiation in physics is a probabilistic process. It's a process that we cannot predict with certainty. We can give probabilities, but it might, for example, in this case, it might emit radiation after 1 second, it might emit radiation after 1 year. All of those are probabilities, but I'm exaggerating the number just an example. So, from the principal point of view, we are not, the cat is in a superposition of both alive and dead at a certain time. What if solving the Schrödinger equation would give you 2 states for the cat, live and dead, with certain probability. Erwin Schrödinger proposed this example not to show that quantum mechanics breaks the laws of logic, but his purpose was to show the strengthness of quantum mechanics, not to say that there is that the cat is dead and alive at the same time. He was not referring to that. He was using that factor to show the strengthness of quantum mechanics, not to claim that that quantum mechanics allow a contradiction. Maybe we can talk about this more and more in the end, but no, we don't have that. From our knowledge perspective, we can't determine whether the cat is dead or alive. However, ontologically speaking, so in reality, truly, the cat is either dead or alive at a certain time. It can't be both states, ontologically, in reality, in existence. Okay. Although quantum mechanics give you superposition of a state, but in reality, when you do a measurement, it would collapse to a single state. So, principle number one is the principle that guarantees that the cat won't be alive and dead at the same time. The principle of non-contradiction. مبدأ عدم التناقض بالعربي. It's a so fundamental principle that we think using it. We are built we are born with this software installed in our minds from birth. So formally speaking, it says it is false that a statement A and the negation of A are true at the same time. So A could be a statement that says that the sky is blue, and the negation of A would be a statement that says the sky is not blue. This principle says that A and so it's basically said that it is false that this statement is true, and this statement is true at the same time. Two trivial have to be stated, and then we can write it symbolically using this in symbolic logic as well. And then there is another principle, which is the principle of self-identity. It says that A is and only is A. Too trivial to be stated, I know. But working with quantum mechanics, we have to be very precise in our thought. Actually, logicians say that this principle can be derived from this. But for practicality and clear of thought, I included both. So those two axioms are from logic, and then from physics, third axiom said that the natural propositions or theories must obey axiom 1 and 2. So any theory about the reality, about the natural world, should obey axiom 1 and axiom 2. Meaning that, any theory should not have a contradiction inside it, and should also obey the principle of self-identity. Okay? This is the words of Immanuel Kant. Immanuel Kant, in his book, the German philosopher, tried to prove this statement, the axiom 3. So he did not take it an axiom; he tried to prove it. And the seminar will take it as an axiom, and we will not prove it. So basically, the statement says that the natural world is logically structured. You cannot find a contradiction. If your theory has a contradiction, then there is something wrong in the theory. You are not applying it correctly to it. Your theory does not correspond correctly to the natural world. Okay, so fourth axiom is the axiom of measurability. It says that we are able to measure observables like momentum, position, energy, and so on. It just gives us the ability to measure. It's the mere statement. It doesn't say more than that. It doesn't talk about how certain or uncertain we are about the measurement process. Okay, so we are fine here. before going to the fifth axiom, which is a set of axioms from mathematics, I want to elaborate on, give an example and elaborate on something from the old theorem of calculus. People before the definition of limits, which is really a modern definition of calculus, they were doing calculus in another style, Newton and Leibniz and those guys. So we will take this example. Imagine we have a function y equal to x squared, and we want to obtain the derivative of this function, dy dx, using the old integral theorem of calculus, not using limit definition. So using limit definition, you just multiply the 2 and then it will be 2x, straightforward. In the old days, they did not do this. They did it in another style. So y would change from y to y plus dy, and x would change from x to x plus dx. This is sorry. This is dx. So the derivation that I'm going to do is in Leibniz style. Okay. So now we can substitute this and this in the original equation here. So this here and x squared there. Y plus dy. Okay. Well, then we can expand this term. It will be x squared plus 2x dx plus dx squared. Okay. Because d and dx, okay, so I forgot to say that. Dx and dy are called integral parts of that quantity, of dy in this example. Very, very, very small part of y, but it is not zero. Okay, so rewriting the equation down here, y equal dy plus dx itself is a small quantity. Dx squared will be much smaller quantity. So we can set it to 0. This whole term we can set it to 0. This is step. Let's call it step 1. Of course, we did some steps before, but we'll start counting from now. We can substitute for y from the definition of y. This y would be x squared plus dy plus 2x. Okay. Now we can subtract the x squared from both sides. This would go, and we would remain with dy equal to x. Yes, to x dx. This is step 2. We can divide by dx. Okay, so this dividing step we call 3. Step 3. Same result as we would obtain with the definition of limits in calculus. But the interesting thing is when we go back to our steps, from step 1, so from step 1, we assumed that dx squared is 0. This would imply that dx itself is 0. From step 3, we said that dx, we divided by dx, so we assumed it is not 0. From step 1, those two implications, we can add them together because there are 2 steps. We did them in our derivation. So dx is 0 and dx is not 0. Okay, so this is a statement. It's a clear contradiction.
تناقض صارخ.
It's a contradiction that hits our derivation. It runs our result. This invalid, not invalid, but we lose trust in this result. From axiom 1, actually, this and this are contradictions. So you can define this A, and this is a negation of A, not A. So this whole statement will be false. A clear contradiction. So it's not allowed by axiom 1 in this analysis. This is how Leibniz and Newton did calculus before. There was an internal contradiction in that theory. However, mathematicians nowadays, so it's a clear contradiction there. Mathematicians nowadays use the definition of limit to avoid that contradiction. But the definition of limit, the definition of limit, this definition, it's a modern definition, very, very, very modern. It's not very old. Okay, rely on epsilon delta definition. It's written for all epsilon more than 0, there exists delta, blah blah blah. This definition relies on the properties of real numbers. Okay, on the existence of real numbers and their properties. So calculus uses the epsilon delta definition of limit, and epsilon delta definition of limit uses the real numbers. And the real numbers in mathematics are constructed in axiomatic set theory. So for us to accept this, we have to accept all of the axioms of set theory. There are 9 or 8 axioms plus the ninth axiom, which is the axiom of choice. So we have now in this. We will assume that the derivation that mathematician did is true and valid derivation, and there is no internal contradiction as happened in the old calculus theory. Okay, so axiom 5 is just the set of axiomatic set theory. It's an 8 axioms: axiom of infinity, axiom of power, axiom of power. Anyway, we would assume all of them to be true, and for this definition to be valid. Otherwise, we can, and we would trust mathematicians that their derivations are valid and so on, which is not always a good idea to do. Trust mathematicians. Okay, so we would assume those set of axioms to be true. So our axiom 5 is all of those axioms, because they give validity to calculus. Okay. Now 5 axioms are completed. Now we can proceed with the analysis. Imagine set X. Set X contains 3 numbers, and set Y contains another 3 numbers. And there is in mathematics, a function is just the relation between elements in X and elements in Y. So a function in mathematics is just those lines. It's the connection line. For example, it can be, in this case, it is x squared. Of course, not only that. It's not only a relation, it's a constraint relation. There is a condition that for every x here, it corresponds to only one y. There is a condition. Not any relation can be a function in mathematics. Okay. So imagine a particle propagating in space with some energy. Using axiom 4, which is axiom of measurability, that says we can measure particles and measure observables of particles. We can construct for this particle at time 0 seconds, we can relate it with 0 position, and then at 1 second might be at 2 meters, and then 2 seconds correspond to 4 meters, and so on. Okay, so we use an axiom 4 because it allows us to measure things. We can construct function of position. Okay, that relates position the different times with different position of some particle. Okay, so it was in the previous example there was number. Now I'm taking out the numbers. So instead of 0 second, I substituted t corresponding to x of t, t plus tau corresponding to x, t plus tau, and so on. Okay, so from axiom 5, we said that the definition of limit, the derivative that rely on the definition of limit is valid. So we can construct our velocity function using axiom 5, both axiom 5 and 4. So velocity is just the derivative of position with respect to time. Okay, so to construct this set velocity, we have to substitute for each velocity element. We have to substitute x, t plus tau, and or minus x of t, and then you see you have to substitute two elements for one element in velocity. So V2 should take two elements from here, this element and this element, and for V3 we can take one element here, but it's not enough. You have to take a second value. So we would do a measurement in x, and then two elements. The idea is, I think it's clear now. Okay, so we can construct our velocity function that takes two elements. This is very important. It takes two elements, and it takes from x two elements and to one element in b. Hence, by this definition, for a single measurement of x of t, velocity is not defined. So for a single element in x, there is no velocity. There is no corresponding to a velocity calculation. Okay. So position, by definition, is a point coordinate, while velocity is an interval, not a point coordinate. Okay. As we try to measure velocity, we will lose completely the position of the particle because it will move a distance, and we cannot predict that distance because it has because we don't have a velocity value. So restate it again. To measure velocity, we need to measure two positions, and when we do the measurement of the position, then we will lose track of the and compute them. We will lose track of velocity. So we lose track of the position of the particle because you are taking an interval. You don't have an idea, and to predict that distance to the particle taken, you have to input another velocity, and so on, which is unknown. So the basic idea is that the uncertainty principle, the idea of inability to measure velocity instantaneously with position came from come from only this definition of velocity. If you are living in Laplace state, if you see this definition, you should realize there is a limit to your measurement purely by looking at the definition, and you are not required to do this limit definition just by knowing the notion of velocity as Newton have proposed it. Okay, so there could be an objection. If someone said that we can give a function of position as a time which is dependent on time, give it in a time. Then we can apply the same formula, which is velocity formula, and we will obtain an instantaneous velocity. So we can measure velocity and position in the same time using this equation. We could obtain an instantaneous velocity value. The reply to this objection is the problem of induction in science. an average of a human, a life of a human being, we observe sun to rise from east and sets in west daily, generation. If you ask your father, he would say he said the same. He saw the same thing, and your grandfather says saw the same thing, and so on and so on. Okay, and also we observe ravens to be black all the time. Okay, Hatcha, did anyone observe a red raven, for example, and a raven with another color? So we could ask a question then. Is it by biological necessity that the sun tomorrow would rise from east and it sets in west? Or could we wake up and see it rising from west? Is there a necessity, a logical necessity? Actually, according to some calculation, astrophysics, the sun, when the helium fuel finished, it would expand and would reach the Earth, and we would see it rising from west. And also, there is white ravens. There is white ravens. It's very rare, but there is. You can. It's recorded in history, and it is well documented. Due to mutation, and a mutation in biology is a phenomenon. It's feasible by quantum tunneling, by the way. So if there is no quantum tunneling, there will be no mutation. So, on a serious note, if we have certain conditions, and from those conditions an event A happened, does that imply that when we observe the same conditions after some time or in another place, that event A have to occur with necessity, or it could not occur with the same conditions? This is called the problem of induction in science. It hits the core of science. Doesn't make it invalid, but it takes some of the strength that's there. So, using this argument of induction, giving a priori or giving a function of position in this form of some particle is invalid objection to that analysis, because what guarantees that the particle would follow this equation? There is no guarantee. It could follow it for a certain path and then diverge. You cannot say it's constrained by, it will be constrained by this equation for the entire lifetime of that particle. Okay, so this objection is refuted. So providing a priori function of velocity won't solve the problem. Giving a function of velocity before in a paper and claiming that a certain particle would follow that, it won't solve the problem. So velocity for a single measurement of position is not defined. That's the core idea. It is according to our five axioms. It is undefined by the definitions and statements of the five axioms. So the uncertainty principle in its general concept can be deduced from classical definition of velocity and position without referring to any quantum mechanical notion. I did not use any notion from quantum mechanics, did I? Yet I didn't provide a quantitative relation. I didn't say delta x, delta b is larger than h bar over 2. So, and that principle is an inherent property of nature. It is you cannot get away from that. Okay. Also, this analysis, that what I did, holds regardless of whether you adopt wave particle or wave nature or a particle nature of matter. It's applicable to both. Why? Because in quantum mechanics, if you want to measure momentum is given with this equation, h bar over this is the equation. h bar k, and k is away is 2 pi over L. This is k. So if you want to measure lambda, you have to take because of awakening, you have two points. Awake could be like this. So you have at least to know B, the momentum, you have to at least take two points. The same idea. There is a dependent of this take in two x's. Let's say to compute the momentum, you have to use x1 and x2. Could be x1 and x2. So this is the same analysis applied in quantum mechanics. It is the beautiful that you can apply it using wave nature of matter or particle nature of matter, as I did here. Okay. But there was a question: why such an analysis did not appear before quantum mechanics? Because all the definitions that I use can be deduced from classical mechanics, can be interpreted using the formalism of quantum mechanics, of classical mechanics. But why we did not hear anyone shouting that stop, you cannot measure momentum and position at the same time with infinite precision as well? Why there were no objections to the idea, to determinism in nature? Well, my view, at least, is that classical perception of the world is as if the world was elementary continuous. The continuity of the physical quantity of energy, momentum, position have hidden this uncertainty principle or such an analysis in any form. Of course, quantum mechanics showed us that the quantum jump is related with h bar, jump in orbits. So it is reasonable to assume that the limit of measurement x and b is related with h bar. Okay. So this is the final principle, but it is deduced from quantum mechanics. In my analysis, I did not provide any equation like this. To provide such an equation, you have to do physical theory like quantum mechanics. Okay. Few weeks ago, I was on YouTube watching. So Prof. Hamood Alharthi have a seminar, and it was related with quantum mechanics and the principle of mind, or logical principles. Prof. Hamood have introduced, not only in this seminar but in his other seminars, he reintroduced an old Kalam principle, which is the principle of recreation. This principle says that particles or objects don't last 2 seconds, 2 successive seconds. They get destroyed and then they appear. Destroyed and then they appear. So if a particle moves in this direction, it will be destroyed here, appear here, destroy here, appear here, and so on. So the Mutakallimun did not provide, and they were not doing physics. Prophet Muhammad have taken this idea, the Kalam idea, and he proposed a relation of the frequency of the recreation. Okay. He verbally stated in that seminar, and I took it in 2 steps. The Heisenberg that equation has appeared, but unfortunately, because I didn't find that he didn't publish that yet. He couldn't put it here. But from merely adopting that idea for recreation and setting an equation for it, the uncertainty principle would follow directly from that. It is a strong evidence that the recreation idea of the Mutakallimun have at least some sense, but it's not necessarily that the theory is correct. It needs more derivation and theorizing and to support it more and more. But quantum mechanics will not provide us with this equation, and we experimentally measure this equation to be correct. However, it might be that quantum mechanics is the current formulation of quantum mechanics is an emergent theory of another theory. It could be, because we have a lot of problems in quantum mechanics. Okay. Of course, on a technical note, physicists do a generalization of the uncertainty principle. It is not only momentum and position. You can have another quantities related with you can apply the same analysis here to another physical quantities. So in general, if A and B, the operators, if the operators of an observable A and another observable B, those operators, don't commute, then you have uncertainty between those two quantities. If they do commute, then you don't have uncertainty. This would be zero. This would be zero, and then you can measure both quantities with instantaneous precision. Okay, so did I skip that? This is from ChatGPT. I think it's clear. So yeah, in the Hamiltonian momentum they do commute. So there is no uncertainty between them, and the Hamiltonian and position don't commute. So there is an uncertainty relation between them, and there is also for angular momentum and so on. So this is the note that I want to elaborate. Actually, I found out. So this is a wave function that a superposition of infinitely many waves. It's a Gaussian wave bucket that represents a particle, and we gave it. This is a simulation. We gave it an initial momentum energy. So it should propagate in this direction, but so it is propagating correctly in that direction. But and this is the probability density. This is x-axis. There is something weird going on. It's better to see it. So it is propagating in x, but the probability gets flattened. We are get flattened with time. You can see that directly from the equation, but when I saw this, I was very surprised. Why? So because it's getting psi square is getting flattened, so it means that we have a wide range of probability in the x-axis spectrum. Our uncertainty in x is increasing with time. It was very weird. So our uncertainty delta x increases with time. Does it mean shouldn't delta b momentum decrease with time? Okay. I had a look. So okay. Just open the book, a book of quantum mechanics that I haven't straightforward. The answer was there. Using Fourier transform, we can transform that side in the x space to a momentum space, and phi is a function of momentum and and time. This is the temporal term and a spatial term. They are multiplied. This is t time, and there is no t time term here. So and phi k0 is giving with this equation. It's a Gaussian wave packet. Okay, so to plot phi, we can't plot this because it has an eye. We can't see this. We have to take the phi square, and the same what we do with psi square. So if we take the conjugate of this and multiply it, the t term would vanish. There will be no t term. The phi square, the momentum equation, won't depend on time. So that's straightforward. If you plot it, it should be stick in time. Should not. There is nothing happening. It's actually looping in time, but there is nothing happening because in the phi equation there is no time dependence. So still there is our x increases, delta x is increases, but the momentum is not decreasing. That's because the uncertainty is not uncertainty is not a conserved quantity. It can increase without bound. We can until a complete ignorance of the system. The uncertainty relation is an inequality. It's not an equality. So just if you realize that it's an inequality, then everything clear. So delta x can increase without bound to infinity, and this equation will be to one value because it's an inequality, not equality. There is no equal sign here. So delta x can increase without bound, and delta b is fixed. But why delta x itself increases with time? The answer is not. The answer is not. Sorry, the question is not answered. Okay. As a small illustration, it's straightforward. This is psi square, okay, and this is x. Froze it with time. This wave function is it's a Gaussian wave packet, represent a probability. It's a summation of infinitely many waves. So it's a free particle. It's a wave Fourier transform. So there is infinitely many waves superposing and constructing this function or wave. When you start the simulation, you give it a certain momentum in the beginning, and you, because there is uncertainty principle, there is something called uncertainty principle. There is the momentum that you give. There is for each wave. So some waves could have higher momentum than the mean momentum that you give. Some wave could have a lower momentum. There are infinitely many waves with, but the momentum is big. The average momentum is around this. The average of the wave, the momentum of the wave scale. But some waves have little bit higher momentum. Some waves have little bit less momentum than the average. That is because that's enforced by the uncertainty principle. Okay, so this is just a graphical illustration of rigid plotting here. Some waves have slower momentum, others have higher momentum. So the result will be that those with little bit higher momentum would propagate much faster than those with the lower. They have almost the same, but there is small initial uncertainty in momentum. Some of them have little bit higher momentum. So as they progress in space, one of them will precede the other. So the result would be this function would flatten. This wave equation would flatten with time. Okay. With time, the higher momentum waves would stretch the wave bracket, hence the uncertainty increases. Okay, so to conclude this note, the uncertainty principle is not a conserved quantity. It can increase without a bound to infinity. So you will be after time goes to infinity. You will be in a complete ignorance. You don't have any information about the system as time goes to infinity. I'm going to write this as time approaches infinity, then your information gain will be zero. The information gain goes to zero if you use okay. And the only way to decrease that uncertainty is to do a measurement again. So if you do a measurement of that flattened wave, you would peak it. You would confine it in a certain space. Of course, still there is uncertainty, but it's better than a complete flat. So it could start, the wave function could start in this, like this. After a while it would be like this. After a while it would be like this. After a while it would be straight line, almost a straight line. You basically, in this case, you have no idea where the particle would have, because it has an equal probability in space. This is the complete ignorance what I was talking about. So it have the width of this wave would be the delta x will be infinity, and the height will be almost 0. So if you integrate psi squared in this case, it should always be 1. It is normalized. So it is like the inverse of Dirac delta function. Dirac delta function is peaked infinite toward infinity in the up, but this is peaked in the x-axis. And both their integration, both Dirac delta function and in this case, psi in this case will be 1. Okay. So the reason that delta x increases with time for a free particle is the initial uncertainty in momentum. It is not because the momentum, the uncertainty in momentum increases, but it is because of that initial uncertainty in momentum. Okay, and delta b itself does not increase with time. This is those two notes are related with a free particle only. Those two notes are general for any quantum mechanical system. So, thank you. Any questions?
أول مشروع حمود على طرح رائع وواضح جدا. فصلت ما شاء الله في الميكانيكا الكمية، بس أول ما دخلت المحاضرة قلت بأن نعود دائما إلى الأصل، إلى أصل الإشكال. بعد ذلك ذكرت بأن أول شيء يلزمنا قبل أي بحث بأن نعرف المصطلحات تعريف واضح. هذه المقدمة الأولى. المقدمة الثانية، المقدمة الثالثة أعتقد بأن أي إشكال رياضي يعود إلى إشكال لغوي. هذه المقدمة الثالثة. الآن وين الإشكال؟ يعني اللي أعتقد أنا الإشكال في الزعم بأن الرياضيين وقعوا في تناقض. بس تسمح لك أصبر شوي. الزعم بأن الرياضيين وقعوا في تناقض بأن لما كنت تسوي الاشتقاق أثناء الاشتقاق دي اكس طبيعتها صغيرة، إذا دي اكس تربيع أصغر، إذا أهملتها. لكنك ما قلت صفر، قلت هي قيمة مهملة. قلت أهمل، يعني نحن نهملها لأنها قيمة مهملة. الآن هل القيمة المهملة هي صفر؟ لازم نعرف يعني القيمة المهملة يعني صفر. فإذا ساوينا هذين التعريفين بأن كل قيمة مهملة هي صفر وكل صفر هو قيمة مهملة، فنقع في التناقض بالفعل. لكن لا أعتقد بأن هذه القيم متساوية.
نعم، لأن نحتاج أنها تكون 2x we'll have to set it to 0. لما خليتها 0 dx square أنا قلت خليتها 0، بس يمكن in another derivation someone would say it is almost 0, it's not 0, but we can neglect it. As we do always in physics and math, if you say that and you neglect it, and you cross it, and that your step implied by a logical necessity that you are setting it to 0, although you are contradicting.
بالضبط هذا اللي أقوله، لأن نحن ما ممكن دي اكس تكون صفر. يعني 2x ما بالضبط، يعني دي اكس ليست شرط ضروري علشان نحصل على 2x، لأنه لو كان شرط ضروري بنرجع إلى التعريف الحديث الليمت في المقام يوجد دي اكس، الفرق في اكسات، الفرق في الاكس. إذا كان بالفعل دي اكس، لاحظ، إذا كان بالفعل دي اكس شرط ضروري يتحقق 2x، إذا بالعودة إلى التعريف الحديث اللي المشتقة موجود في المقام بالدي اكس. إذا كان فعلا شرط ضروري إذا نحن نقسم على صفر. اللي يضمن وجود 2x كقيمة للاشتقاق هو ليس فقط اتصال الدالة يعني continuous، ولكن نعومة الدال بالعربي نسميها سموث فانكشن، هذا اللي يضمن وجود 2x. أنا أعتقد بأن هذا يعني مجرد ملاحظة بسيطة.
هل تشوف أن طريقة لايبنز هذه فيها غلط منطقي؟
لايبنز ما سوى، ما قال بأن النيجليجبل يعني صفر. شوف هنا يعني اختلاف لغوي.
حتى لو فرضت انه عشان تطلع لك 2x، حتى لو فرضت لو قلت انه نقدر تجاهل النيجليجبل قابلة للإهمال وكملت الاشتقاق، لأن أنت في التحليل النهائي والأخير ما شفت عليه يعني خليته زيرو بالضرورة بتوصل.
هذا من عملي في الحل، لكن ما ضروري في فرق. الآن الفرق ما بين هل لأن استعملناه معناته ضروري هذا الفرق، لأن مثل ما قلت لك إذا
ليش ما يخليه ضروري؟
لأن إذا قلنا ضروري فعلا ضروري للحصول على 2x.
أنا على تعريف أنا من فقط لتوضيح التناقض.
قد يكون
أنا ما قلت أن الخطوة الأولى فرضت شيء، الخطوة الثانية اللي بعد المتأخرة فرضت شيء آخر، لكنه عشان نوصل لل 2x يعني أنا أفرض يعني أقصد البرهان بالتناقض في الرياضيات assume A، لأن أنت تريد تثبت A assume not A. By assumption you are setting that. عمليا اللي سويته أنا أو هذا من اللي أنا سويته، اللي كانوا يسووه هذا عمليا كانوا يشطبوه. إذا ما شطبتها ما يعني بيبقى ترم هناك، بيبقى أنت want be only 2x في ترم ثاني إذا ما شطبتها. ما بيعطيك اللي يوصل للتعريف الليمت. تعريف الليمت منضبط ينبني من مسلمات نظرية المجموعات ينطلق منها. ما تقدر توصل لأنك يعني بالصرامة الرياضية اللي كان حتى نيوتن أساسا كان شايف، يعني نيوتن ولايبنز كانوا شايفين هذا إنه في عدم اتساق في النظرية. لهذا نيوتن ما كان مهتم ينشر الكالكولس ويدعي إنه هو سواها منذ البداية، لأنه كان يشوفها حل عملي فقط، بس إنه رياضيا الإشكال هناك يضرب في صميم التناقض، وما تقدر تطلع منه إلا إنك تقول يا إما هناك ما في تناقض، ما في يعني يا إنك مثل ما قلت ما تحطها زيرو، لكنه بيكون هنا ترم زائد إذا it's not 2x يعني إذا كان هناك ترم زائد.
شباب مثل النقاش بالعكس. عندي سؤال، تريد توصلنا يعني لإيش باختصار بهذا الاسم؟
Always when you have a problem, refer to your fundamental definitions and axioms. So يعني هذا كان مقدمة أو إنه تعريف بأهمية الإنساق المنطقية، يعني أهمية دراسة الرياضيات يعني foundational mathematics، وإنها لأن الرياضيات تبدأ بمسلمات أساسية وفي وضوح في التفكير. في الفيزياء ما عندنا هذا. في الفيزياء مثلا لما نقول مرة ويف مرة لا دكتور جمع في الفيزياء مثلا ويف بارتيكل ديفايد، مرة تقول إنه ويف مرة تقول إنه بارتيكل، وبوث هاف contradicting natures. هذا localized هذا يعني منتشر في الفضاء. اوكي صح، انت تقول مره هو يتصرف كذا مرة يتصرف كذا، انت طلعت من تناقض بهذه الطريقة، بس ايش يبرر هذا فيزيائيا؟ ما اتكلم عنه، بس ايش يبرر هذا فيزيائيا؟ فاعتقد ان علينا اعادة النظر في اسس الفيزياء الاساسية، اخذها بتعاريفها الاساسية، النظر في ما تقول ما تزعم هذه المسلمات الاساسية، وايضا اعتقد علينا اقتناص التناقضات من ثم الانطلاق، والا لان الكوانتم 100 سنة مر عليه عنده مشاكل في اشياء ما قادرين نحسبها، معالقين في يعني هناك ما قادر تفهم النسبي للعام. ربما هذا سبب انه ما حللنا نظريتنا ومن اصولها الرياضيه ومنطلقاتها الرياضيه ما حللناها فلسفيا، لانه صار فقط شتم الكالكوليس. هذا اللي صار معنا. يعني ما في لا فرق هذه فيزيكس يعني وورد وايد اشكاليه الفيزياء عالميا انا حاليا الرجوع بعض الشيء والنظر في في الاسس الفلسفيه لما نقوم بالرياضيات هذه ومحاوله تفسيرها و حفظ التناقضات الداخليه هناك كثير من التناقضات. اينشتاين كان ما يعني لما كان يحاول في الفوتوإلكتريك كان تناقض فهو كان يحاول شاف التناقض يعني كانه وجبه بالنسبه له راح اكلها حللها وكذلك النسبيه العامه مثلا وتحويل النسبيه الخاصه في العام الخاصه بالذات كانت بسببها تناقض في النظريه الكهرومغناطيسيه والانرشال فريمز وهذا من هناك بدا ف you have to observe and you think يعني تفلسف النظام يعني اقصد ان الفيزياء ليست رياضيه. سؤال ثاني شباب؟
نقدم مسألة مناسب خير
ان شاء الله.
هذا شباب ماشي.
So what was first, the math or the physics?
was philosophy historically.
سؤال واضح.
And what circles?
All this math, all this physics that you are talking about, so the math they put math in the top, combine the two. The math was first. So all the sheets, all these theory they were before the physics, the quantum mechanics. So then you put them in the top. So it's just a model, it's an axiom. So it's not.
Yeah, it's not يعني هذا البروسيس not one directional process. You throw math.
The math exists before.
Historically yes. No, even historically not quite.
فلسفي ولا فلسفي؟
No.
فلسفي ولا تاريخي؟ ما existing before.
تاريخيا تقريبا إذا تروح أيام المصريين واليونان ما يحتاج فلسفة يعني ما not straight forward answer بس إنه أقصد أنا ممكن فهم غلط إنه فقط أقصد إنه المبادئ والمنطلقات الفلسفية والنظر الفيزيائي يعني هذا الحدس الفيزيائي هو اللي هو اللي يسبق it's not one way يعني it's a dialectic process عملية قدرية you propose math think about it derive things conclude think again يعني فتطبق مرة you are theorizing and you are deriving mathematics يعني خطوة قدرية يعني مع إخواننا
If delta x is 0, then delta x will be 0. So what's the difference between dx and delta x? This is, by the way, not dx squared, it's dx, the whole square.
دي سكوير اكس اكس. آخر حاجة.
Yeah, not x squared, it's the whole.
So what's the difference between dx and delta x? There's a difference, right?
Yes, there is a difference. Practically speaking, they were doing this. I am not doing this. يعني
This is
أقصد
physics or math?
sorry.
So this is physics or math? Here, those are physics or math?
Math.
Those are math.
Yes, pure math.
There is no relation between delta x that you see there and this dx.
Which
So
is
you
the
put
text?
So you put the physical phenomenon on the top of the math. So the math was before, and then you try to explain. But you come back to the quantum mechanics. In any case, you come back to the quantum mechanics. So there is a limit between classifier and the quantum.
Exactly. But the mere statement of this seminar was not to propose a quantitative relation of the answer. It was only to show it.
At the end, you talk about the spin. So sigma A, sigma B, and you talk about permutation.
That came from the theory of quantum mechanics.
True. It comes from the math, not from the quantum mechanics. So quantum mechanics, they put it on the top of the math to explain it. So Hilbert space, Hilbert. So
Yes.
he's a mathematician, right?
Mathematician.
There's no physics. They put the math, whatever quantum mechanics. So the math was at the service of the physics.
Exactly. I am not proposing you can work independently of math. I am saying that this dialectic, it can't be only one way a mathematician work and تسمي نفسك فيزيائي. You have to do math at the same time you do your physics.
This is what they did. So the math was there, and then they come up with the physics to explain the physics. You want to know the physics. So they did that too.
دكتور تعرف قدرية هيجل the same concept you can think with نفكر بنفس الوقت إنه هذا يعتمد على هذا وهذا يعتمد على هذا طبق هذا طبق هذا طبق. It's a joint mission, not only physics or philosophy or it's a joint. مشكورين جماعة جزاكم الله.